Hello again, everyone. So last time we were talking about how to set the cell up and like what goes on what side and what the reactions are going to be. Today what we're going to talk about is how much. Yes, electricity is going to flow, but sometimes with electricity, we care how much electricity is going to flow. Now, there's a lot of different properties we can talk about with electricity if we really wanted to. We can talk about how fast the electrons are going, how hard it is for them to get through this thing up here. But like I talked about in the doc you worked on yesterday, the property we're going to talk about is called voltage. And what it is it's a difference in electrical potential energy. So it's a lot like talking about waterfalls. You might be way up high in the mountains and have just a little bitty teeny tiny waterfall like in the middle of a river. Well, the water only has this much difference in potential, and so it kind of flows down the waterfall. And it really doesn't care at all the fact that it's up in the mountains. Or you might be just about close to the ocean and see that you've got this huge waterfall where it falls this much. Now this is a lot bigger potential difference, even though it's down closer to the ocean level. But when we go to measure things, it's really hard to compare those. How do we figure out how much potential energy a piece of copper has? How do you figure out how much potential energy a piece of zinc has? Well, the easiest thing that we can do is, like these waterfalls, go back to comparing them to something. We talk about measuring mountains in difference from where they are at sea level. So the base of the mountain might be here and the top of the mountain is here. And we know this is this elevation A, and this is elevation B, and we find the difference between those two. It's the reason why Mount Everest, even though it's the tallest mountain in the world, it's like this high, is indeed not the biggest mountain in the world. Biggest mountain in the world is Mauna Kea, but it starts at sea levels here. Mauna Kea is like here. The top isn't very, very high in the air, but the difference between where the bottom is and where the top is much bigger. So that's what we're going to look at with these chemicals is we got to choose something that's sea level for us, that's going to represent sea level. And what we go with, what they choose to work with is how do they compare to what's called a hydrogen standard cell, which is just, frankly, a container of acid sitting here with a piece of graphite or something in here that would conduct electricity and that is going to make hydrogen gas when we run this through. If we hook the hydrogen here, electrically, how does it compare? It's not important that you understand what that hydrogen cell is, just as long as you understand that what we're going to do is we're going to take all of the metals that are out there and we're going to compare them to this hydrogen cell and see how they work. Okay, and when we do that, what we can end up with is one of our favorite things in the world, a table. Yay, tables. Okay, a list of information. Now you come down here to this right here where I take 2 hydrogen plus 2 electrons and it produces H2 gas, and it has a reduction potential of 0. Okay, what this means is how likely is this element right here to be reduced when hooked up to a hydrogen cell? Well, clearly it's not, because it is the hydrogen cell. Okay, some things are likely to be reduced. These things are likely going to happen. Silver is going to turn into silver metal, and iron is going to turn into iron metal. And then we get down here to these other things that have negative reduction potentials. That means that if you hook these up to something, most likely they're going to be the oxidation side of matters, and this is going to be the reduction side. Okay, so how do we decide what the potential is of a cell? For example, our magnesium and our copper cell here. Well, basically what we need to know, like the height of the mountain, is what is the difference. If I hooked the magnesium up, okay, we're looking for this. We know that this reaction here, as we said several times, this is going to be our oxidation. Okay, and this is going to be, this copper right here is going to be our reduction. So we're going to slide that up. We don't care about the picture anymore. Okay, copper 2 plus 2 electrons is going to become Cu. So, and this is our reduction. Now again, our table over here, it only gives me reduction potentials. So I can find the copper, the reduction, and I've got copper 2 plus over here, and you can see, I know it's kind of small, but this is a 0.34. So we call that E stands for energy, not. The 0 up here is not N-A-U-G-H-T. It means standard, it means basic. Okay, and this is for our reduction cell, okay, was equal to 0.34 volts. Well, the E naught for our oxidation, you'll notice when we come over here and we find the magnesium here that this is a negative number because this isn't going to be our oxidation, it's going to be our reduction. Or try that again. This is a reduction potential and we're oxidizing this thing. So we're going to write down this negative 2.37. Am I looking at that right? Yeah, negative 2.37. And then we're going to find the difference between these two energies. So the equation we'll use is the energy total will equal the reduced potential minus the oxidized potential. Okay, ignore that dot. So we've been through this before. Write out your equation, put your numbers in. So 0.34 volts minus a negative 2.37, sorry about that funky negatives, volts is going to be equal to, I didn't think of how to look up a calculator, so give me a second. 1, carry the 1, 2.71 volts. Okay, will be the potential for a cell between magnesium and copper. Now your question is, what if I have more magnesium? What if I had more copper? What if it was really, really concentrated magnesium sulfate and really concentrated copper sulfate? And we had a huge piece of copper and a huge piece of magnesium, and the answer is it does not matter. It doesn't matter how wide the waterfall is. It only matters how high the waterfall is when we look at difference in potential energy. So the potential of this cell is going to be 2.71 volts if it is made out of magnesium and copper. And it does not matter anything else about this cell. Now, if you went and looked up batteries, like I asked you to yesterday, and you happened to find those voltages, you may have discovered this for yourselves. If you get out a teeny tiny AAA battery, you're going to see, and I'll see if I can get this to focus on my camera here. I don't know if you're going to get it. Maybe if I move the paper. Okay, if you go get teeny tiny 1.5, AAA battery, you will find that it has a voltage, and it should be right there, even though I know you can't see that, of 1.5 volts. And then we go get a little bit bigger. We go get a AA battery. Okay, and right here, again, probably still can't see that, we'll say 1.5 volts. And we go get a big old D cell battery. I think I can get this one to show up. And right here, it will say 1.5 volts. All three of these things have the same electrical potential. So why do we even bother having three different sizes? And the same answer is simply this one has more chemical in it. This has a lot of chemical, this has a little chemical. So we use AAA batteries in little bitty stuff like your remote controls, stuff that uses teeny tiny little bits of electricity at a time. Whereas you're going to put D cells in things like children's toys that we want to run for a long time, make a lot of noise and do a lot of motion, or in great big batteries that we need to run great big flashlights that we need to power big lights and bright things for as long as we possibly can, because that's what this is going to do. This lasts a lot longer than this thing. So then the question is, what about a 9-volt? Surely that's a different reaction, right? So this 9-volt battery here, okay, this is truly a battery. These things right here, these are all called dry cells. They are chemical cells. They have a one electrode here and one electrode here, and there's some chemicals in here, and there's a salt bridge to separate the chemicals, and they run just like the cells we've talked about. This thing is truly a battery. Now you can see over here already that I've kind of trying to hide that I've done this, but went in and pried this thing open, and that right there is what our 9-volt battery looks like. Okay, see, it's not one, right? There's 1, 2, 3, 4, 5, 6 separate. They're about 4A batteries, or quadruple A batteries, okay, packaged together. So I have the same 1.5 volt battery that I had over here, albeit a much smaller, a little bit smaller version. Same 1.5 volt battery times 1, 2, 3, 4, 5, 6 will give me a 9 volt. If you're familiar with a 6 volt lantern battery, it does exactly the same thing. The cells are significantly larger, and I don't have one to show you, and I've tried to pry them open. The casing's a little bit tougher than the 9 volt, but is the same basic idea. That 6 volt has 4 separate dry cells sitting inside of it. A car battery, a 12 volt car battery, runs a little bit different. The cell is a different set of chemicals. There are 6 2-volt cells in there instead of being like our 9-volt here has 6 1.5-volt cells, and they run a little bit different. But generally, that's how we get that. So, moral of the story, in order to calculate how much potential energy a cell has, we're going to take the reduced side minus the oxidized side. And as a hint, if you get a negative number, you have your reduced and oxidized elements backwards. Okay, all you have to do is change the sign of that number and go back and fix the way you had your cell. Okay, and I put the table that I've got for you in the classroom under reference, so you can look those things up, and it really is as simple as look up the two and find the difference between them. Watch your negatives. Remember, we're subtracting because we're looking for a difference, but otherwise this is a very, very simple calculation, and I know you guys can handle this. All right, you guys all have a great afternoon. Bye.